The objective of this lecture is to provide an introduction to rocket dynamics. Now, the key results derived in this lecture are as follows. The first is the differential equation that describes the translational motion of a vehicle that is losing mass due to propulsion. So I could say that is thrust. Second key result is the rocket equation that describes the change in velocity due to a change in mass of the vehicle. And the third result is what's called the impulsive thrust approximation, where, given that the thrust is considered to be sufficiently large, we can describe that change in velocity as occurring instantaneously. We'll get into all of these different aspects in this lecture. So the first part of this is to describe the motion of the rocket. So imagine we have a vehicle, which I'll kind of configure, similar to what one might configure if they were looking at a rocket. And that vehicle looks as follows. So, and at some point in time, we just say at some time t, the rocket has a mass, which we're going to say is m of t, and has an inertial velocity, which we'll say is vi of t. Now, the rocket's moving, in this picture, it's moving to the right with this direction, with this velocity vi of t. But we're going to actually look at in order to get the differential equation, we have to analyze the change in momentum of the rocket. So what we're going to do is we're going to look at two configurations. So the two configurations, or I should say the two instants of time. The first one is what I had drawn before, which we're going to call that time t, which is what I called it before. But the second one is actually just as important, and this is going to be the time which I'm going to call this is m of t and vi of t, and then the velocity is pointed, as I said, to the right, vi of t. So this is time t. But then I'm going to do this again for time t plus delta t. So we're going to have the same picture for the rocket, except for now the rocket has actually lost mass in the process of going from t to t plus delta t. So this is important, because at t plus delta t, the rocket actually has a mass m of t minus delta m, and it has a velocity vi of t plus delta v. And this is at time t plus delta t. But in that time, there's been a mass loss. And that mass loss has been by an amount delta m. And the velocity, the inertial velocity of that mass, is going to be denoted as v delta m. So what we're going to do is we're going to do a momentum balance in order to be able to figure out what's going on. So we have to do a momentum balance, which means we have to look at the linear momentum. So let p I of t be the linear momentum of the vehicle. And that at time t is equal to m of t times vi of t. But if we look at it, we have to look at the linear momentum of the entire system. So this is really important. It's the linear momentum of the system at time t. So now we're also going to look at pi of t plus delta t. That's equal to the linear momentum at t plus delta t of the system. And I could actually, make that a little bit clearer up here. This is the linear momentum of the system at t. This is the linear momentum of the system. And again, I'll put it in parentheses, of the system at t plus delta t. Now that's a much more complicated thing, because if you actually look, that's equal to the linear momentum of what I'm going to call the body at t plus delta t plus the linear momentum of the lost mass, which is p delta m at t plus delta t. Again, it's t plus delta t. So this now becomes more complicated because we have to figure out each one of these. So let's look at the linear momentum of the system at time t of the vehicle at time t plus delta t. Well, that's equal to m of t minus delta m times vi of t plus delta vi. Let's put an I here. Delta vi. So now, that's not all of the momentum of the system. We also have this momentum associated with this mass delta m at t plus delta t. Well, that's equal to the mass delta m times the velocity delta m v delta m I. So now we need to figure out what this mass delta m is, and we need to figure out what v delta m is. So let's look at this again in a little bit more detail. Is that we assume that the vehicle loses mass at a rate which I'm going to call m dot of t, where m dot of t is going to equal minus b, which is a constant. And that constant is such that b is greater than or equal to 0. So the quantity b is called the burn rate. So given that the vehicle loses mass at a constant burn rate, we are actually able to write m of t plus delta t is equal to m of t minus b times delta t, which implies that delta m is equal to b times delta t, because that's clearly greater than or equal to 0, because delta t is bigger than or equal to 0, and b is also bigger than or equal to 0. So as a result, we can write the linear momentum of the system at t plus delta t as m of t minus b delta t times vi of t plus delta vi. That's the linear momentum of the body. And then we've got plus b delta t times v delta m I. But now we have to figure out what V delta M is. So need to determine V delta M I. So we note the following. So let's look at the rocket again. So if we look at the rocket, we see that if we were to decompose that velocity of that lost mass, here's that lost mass, delta M, that we could actually decompose it into the following. We could say that we have what's called an exhaust velocity relative to the rocket, and then we have the velocity of the rocket itself. So V delta M I can actually be decomposed into VEI plus VI of t. Now, what do all these things actually mean? VEI is what's called the velocity of the expended mass delta M relative to the body, or relative to the vehicle. I could say the vehicle. And that implies that the inertial velocity of delta M is given as, let's write it this way, that V delta Mi is equal to the velocity of delta M relative to the body plus the velocity of the body. Right? But that's equal to what I had said, VEI plus VI, because VB is equal to VI and V delta M relative to B is equal to VE. So once again, we've confirmed that this is the velocity of the expended mass, which gives us that the linear momentum at time t plus delta t can now be written as m of t minus b delta t times vi plus delta vi, and then we have plus b delta t times ve I plus vi of t. So now let's compute the change in the linear momentum. So if we take the difference, the change in linear momentum from t to t plus delta t is given as p I of t plus delta t minus p I of t is equal to, well, let's write it out. We've got m of t minus b delta t times vi of t plus delta vi. That takes care of that. And then we've got plus b delta t times vei plus vi of t minus m of t times vi of t, which gives p I of t plus delta t minus p I of t is equal to, we've got m of t vi of t plus m of t delta vi minus b delta t times vi of t minus b delta t times delta vi, and then we've got plus b delta t times ve plus b delta t times vi of t minus m of t vi of t, which implies that p I of t plus delta t minus p I of t is equal to. Well, we can see that the m of t v of t cancels out, and we can see the b delta t vi of t cancels out. So we get m of t times delta vi, and then we've got minus b delta t times delta vi, and then we've got plus b delta t times vei. So now we have everything that we need in order to be able to apply a momentum balance, because now we can say the following, is that we know that pi of t plus delta t minus pi of t divided by delta t is approximately f of t, where that's equal to the force. So as a result, we actually can get the following expression when we substitute in. We've got m of t delta vi, and then we have minus b delta t delta vi, and then the next term is plus b delta t times vei, all divided by delta t is approximately f of t. But now what we can do is we can take the limit as delta t approaches 0. So if we take the limit as delta t approaches 0 of m of t delta vi minus b delta t delta vi plus b delta t times vei, all divided by delta t, that's equal to m of t, or the limit as delta t approaches 0, of m of t times delta vi over delta t, and then we've got minus b times delta vi, and then we've got plus b times vei. And it's important to note here that this limit is actually being taken in the inertial frame, which means we're as viewed by an observer in the inertial frame. And so this is actually equal to m of t times d dt in I of vi, and then the second term in here disappears because as delta t approaches 0, delta v also approaches 0. So we wind up with plus b times ve. That term stays, it survives, and that's equal to f. So we now have the differential equation of motion. So therefore, the differential equation that describes the motion of the vehicle is given as m times d dt in I of vi plus b times ve in I equals f. Now we can rewrite this differential equation in the following way. M times d dt in I of vi equals minus b times ve in I plus f. Now, this is where things get a little bit more interesting. The quantity minus b times ve in I is called thrust. Now you might think that by looking at this that the thrust is actually negative, but the thrust is actually not negative, it's positive. And the reason it's positive is because if we look back at the vehicle again, we actually see something interesting about this vehicle. The exhaust velocity, this is VE, is relative to the rocket. Remember, it's relative to the rocket. VEI is relative to the vehicle and lies in the direction opposite VI. It means that if VI is in this direction, and I'm calling this direction positive, VE is actually in the negative direction. So that implies minus B times VE is in the same direction as VI, which implies that the thrust is in the direction of motion. And what that means is that as a vehicle loses mass, it's actually going to be propelled in a particular direction. If the vehicle is already moving in that direction, then it's going to accelerate the vehicle, which makes perfect sense. So we define minus B times VE and I as T is defined to be minus B times VE and I, which is equal to the thrust. And as a result, we wind up with M times D dt and I of VI equals the thrust plus whatever other force is acting on the body. So that's the differential equation of motion. Now we're going to make a few other simplifications here in order to be able to solve this differential equation. So we're going to solve this differential equation assuming that the vehicle is in rectilinear motion. Well, that means, so that is, the vehicle is moving in a straight line. So, given that, we can actually draw this picture again. Here we have the vehicle again. And we're going to call this direction U. And that's going to be the positive direction of motion. So, now what we can do is we can say, given rectilinear motion, we can write that VI is equal to V times U, and we can write VEI is equal to minus VE times U. And as a result, we have the following equation, which is we get M times D dt and I of VI is equal to M times dV dt times U. And we've assumed here that U is inertially fixed, so because it's moving in a straight line, otherwise it wouldn't be moving in a straight line. And of course that is equal to T plus F. but t is equal to minus b times VEI, which is equal to b times VE times u. And we have F is just equal to F times u, which gives m times dV dt times u is equal to b times VE times u plus F times u. But let's assume that F is equal to 0. So there's no external force. So propulsion is the only force. Then dropping the u's, because we don't need them anymore, we get m times dV dt is equal to b times VE, which is equal to t. So now we actually have a way of being able to express t. So we know that we have that b times VE is equal to t. So now assume that VE is constant. So we had previously that b is equal to a constant. So this implies that b times VE equals t is equal to a constant. So we can actually write this now in terms of t, and we get that m times dV dt is equal to t, which implies that dV dt is equal to t over m. But remember that m of t, or m dot of t, should start with that, is equal to minus b. And since b is constant, we get that m of t is equal to m of t0 minus b times t minus t0. So what we then get is as follows, that dV dt is equal to t all divided by m of t, if you want to call it that, which is equal to t all divided by m of t0 minus b times t minus t0. So now we can actually solve this differential equation by separating variables. So we actually get the we actually can write this in the following way, which is that, recall that b times VE is equal to t, which implies that b is equal to t all divided by VE. So that means that dV dt is equal to t all divided by m of t0 minus t over VE times t minus t0. So now, in separating variables, we're going to get the following. We're going to get that dV is equal to t all divided by m of t0 minus t over VE times t minus t0 dt. So now, similar to the way we dealt with m of t0, assume that v of t0 is equal to v0. So we can integrate both sides. So integrating both sides gives the integral. So we've got v0 to v, and since I'm using v in the upper limit of the argument, I'm just going to call this d eta, is equal to the integral from t0 to t of t all divided by m of t0 minus t over VE times sigma minus t0 d sigma, where I actually am using a dummy variable of integration. But this can be integrated more conveniently if we actually write the integral on the right side. If I multiply through by VE over t, I get t times VE over t all divided by m of t0 times VE over t minus sigma minus t0 d sigma, which is equal to, this just becomes a natural logarithm, but before we do that, let's actually write it as VE all divided by m of t0 VE over t minus sigma minus t0 d sigma, which gives us V at t minus V at t0, because that was equal to the velocity at t0, is equal to, so now let's factor out the VE. We get VE, and we get times the natural log of this result. M at t0 VE over t minus sigma minus t0 evaluated between t0 and t. But because there's a negative sign in the front. So this becomes minus VE times the natural log, let's write it this way, natural log of m of t0 VE over t minus t minus t0 minus the natural log of m of t0 VE all divided by t. And so we can flip the order of the natural logs and also realize that the natural log of the difference of the natural logs is the ratio of the natural logs. So this becomes VE times the natural log of m of t0 VE all divided by t divided by m of t0 VE all divided by t minus t minus t0. And this is equal to VE times, now I'm going to multiply back numerator and denominator by t over VE, and I get the natural log of m of t0 all divided by m of t0 minus t over VE times t minus t0. Now, that's a pretty useful result because we can recall that m of t is equal to m of t0 minus t over VE times t minus t0, which gives that v at t minus v at t0 is equal to VE times the natural log of m of t0 all divided by m of t. Now this last result can be written in the following form. Delta V is equal to VE times the natural log of m of t0 divided by m of t. Oftentimes, the way this is written is we say, so we do the burn from t equals t0 to t equals tf. And in the process, we actually wind up writing this as delta V is equal to VE times the natural log of m of t0 all divided by m of tf. So now what that gives us is this is what's called the rocket equation. And it's a common equation that's used to be able to describe the change in velocity for a given change in mass. Now, the last thing that we're going to do in this lecture is as follows. So we're going to do what's called the impulsive thrust approximation. So the impulsive thrust approximation. So the impulsive thrust approximation works as follows, which is that imagine that I have a very large thrust over a small amount of time. So I'm going to actually draw this picture as follows, which is that imagine that this thrust is a really large value and it takes place over a very small amount of time. So this value t is very large. Now remember, we said that t was constant because the burn rate is constant. And this time interval here, delta t, is very short. So the impulse of the thrust, so this is the impulse of t over delta t, is equal to the integral from minus delta t over 2 to delta t over 2 of t dt, which is equal to t times delta t, of course. But that, if I assume that as this delta t approaches 0, so we're going to make this assumption. So we're going to assume that as delta t approaches 0, t times delta t remains constant. Then what that means is that the thrust t can be approximated as infinite over a 0 duration. And what I'm going to do is I'm going to actually write t times delta t is equal to t hat. So that means it implies, because t times delta t is constant, that the integral from minus infinity to infinity of t dt, which is equal to t hat, is the value that we got from that t times delta t, such that t is equal to infinity when t equals 0 and is equal to 0 when t is not equal to 0. So as a result of that, what that means is that we can change, so this last result implies that velocity can be changed instantaneously. And why is that? And the reason that that's true is because recall that m times dv dt is equal to t. But if I integrate this, so I'm going to integrate this from t equals 0 minus to t equals 0 plus of m dv dt, and that is equal to the integral from t equals 0 minus to t equals 0 plus of t dt, but that's equal to t hat, which means that this here has to be the change in the velocity, which means that m times v at t equals 0 plus minus m times minus v at t equals 0 minus has to equal t hat. which implies that v at t equals 0 plus minus v at t equals 0 minus has to equal t hat all divided by m, which means that we can change velocity. Velocity can change instantaneously. But recall that delta v is equal to ve times the natural log of m0 all divided by mf. So that implies when velocity changes instantaneously, due to impulsive thrust, to what is known as impulsive thrust, we have delta v, which is equal to v, I'm going to call it v plus, minus v minus, is equal to ve times the natural log of m minus over m plus, where v plus is the velocity the instant after t hat is applied, and v minus is the velocity the instant before t hat is applied. And similarly, that m plus is the mass the instant after t hat is applied, and m minus is the mass the instant before t hat is applied. So now we can actually write this as delta v is equal to ve times the natural log of m minus over m plus. And there's one last thing that is worth noting in here, which is ve, which is now what's known as the exhaust speed, because it's a scalar, is actually defined to be g0 times ISP, where g0 is what's known as the standard acceleration due to gravity, and it has the numeric value of exactly 9.80665 meters per second squared. That's not an approximation, that's an exact value. And ISP is what's called the engine specific impulse. And it's measured in time units. In this case, it would be measured in seconds. So VE is equal to G0 times ISP, which implies that delta V is equal to G0 ISP times the natural log of m minus over m plus. And this is what's known as the impulsive thrust approximation. And it's due to the fact that the thrust is infinite due to infinite thrust applied over a zero duration. Now, that basically takes us to the end of this lecture because we've done three things. We derived the differential equation of motion. We then solved the differential equation assuming rectilinear motion and wound up with the rocket equation. And then, after we wound up with the rocket equation, we made the impulsive thrust approximation, which was infinite thrust over zero time, which led us to this last result, which says that mass changes instantaneously due to the fact that velocity changes instantaneously. So, actually, this last point may be worth making, which is that note that mass changes instantaneously because velocity changes instantaneously. So that's an important thing. So if you look at this equation, you've got delta V is equal to G0 ISP times the natural log of m minus over m plus, which could be rewritten this way. We can write delta V all divided by G0 ISP is equal to the natural log of m minus over m plus, which gives that the natural log of m plus over m minus equals minus delta V all divided by G0 ISP, which implies that m plus over m minus is equal to the exponential of minus delta V all divided by G0 ISP, which implies that m plus is equal to m minus times the exponential of minus delta V all divided by G0 ISP, where we note that exp of x is the same thing as e to the x. Means the same thing. We just write it that way because it's just a little bit neater to actually write it that way. And you see this last result, m plus is equal to m minus times the exponential of minus delta V over G0 ISP. So delta V is equal to V plus minus V minus, which is an instantaneous change in velocity, which leads to an instantaneous change in mass. So that's the final result for this particular lecture. We'll pick it up next time when we start using the impulsive thrust approximation in orbit transfer.